Hello everyone. In this video, we will cover several root finding methods that are very practical and handy in solving many problems in engineering, sciences, and finance. There are two main categories of root finding methods: bracketing methods such as bisection and false position methods, and open methods such as Newton-Raphson, secant, and modified secant methods. This is the example that we will be using in this video. Here we want to find the roots of the following quadratic equation. Typically, the solution can easily be obtained using the quadratic formula, and for this example, the answer is that there are two roots, one at x is equal to 2 and the other root is at x is equal to 5. Now, in this video, we will not use any external third-party library such as NumPy. We will only use Python functionality, but for plotting purposes, we will only use matplotlib. So let's import the matplotlib library. So here we create an input array starting from -4 and going up to 8 with an interval of 0.1, and then we write some lambda functions which takes the argument x and then output the quadratic equation, which is x squared minus 7x plus 10. And since some of the methods like Newton-Raphson method uses the derivative of this function, so we will also write a derivative function which is 2 times x minus 7. And then for plotting, we generate these function values for the input array and then plot these. So let's run this cell and the next cell, and this is our quadratic function, and you can see the root value at x is equal to 2 and another root value at x is equal to 5. So now let's see how we could first identify these root intervals or the number of roots. For that, we use the incremental search, and the goal of this algorithm is to find the number of roots present and output the corresponding intervals. We know that if x is real and continuous in the interval, and f of x sub l and f of x sub u have opposite signs, that is their product is less than 0, then there is at least one real root. So now let's see how we can implement this in Python. So let's first import some typing, and then we have this function. It's defined as incremental search. It takes the function, which is a callable, that as an argument it takes the lower bound, upper bound, and then the increment length. So we also need to specify an increment length to search for the roots in the function. So first, our intervals is an empty list, then the number of roots are also set to 0, and then again, while lower bound is less than or equal to upper bound, we evaluate that function. We see if it is equal to 0, then we update it as a root and also update the interval. So in this case, we subtract the increment length and add the increment length for the lower and upper bounds of the interval. So if it is not 0, then we see if the lower bound and the lower bound plus increment length, their product is less than 0. If it is less than 0, they have opposite signs. We could increase the number of roots by 1 and then also append the lower and upper bound of the interval containing the roots to our interval list. And after that, we update our lower bound and repeat the process. So once this loop is finished, we return the number of roots and the intervals. So let's run this, and then we apply this to our function for the range -4 and 8 with an increment length of 0.8, and let's see how many intervals do we get. So we have two intervals, one starting from 1.6 to 2.4 and the other starting from 4.8 to 5.6. Okay, so now let's see how we could use the bracketing methods to find the roots within these intervals. So first bracketing method that we are going to discuss is called the bisection method. It is based on basically divide and conquer approach. So we divide the interval in two halves. The function value is evaluated at the midpoint, so we compute the midpoint of that interval. So then the sub-interval where the sign change occurs, we keep that interval and we repeat the process until we find the root or a stopping criterion is met. So let's see how we could implement this bisection method in Python. So that's the bisection method or bisection function definition. So f is our function, a callable. We have the lower bounds and upper bounds, and then a threshold value, in this case 1e minus 3, and then we also specify maximum iterations in the arguments. And the output could be either a float, that is the root value, or a null value when there is no root present in that interval. So we start with the iteration 0 and we run a while loop where lower bound is less than or equal to upper bound. As long as this condition is satisfied, we continue these iterations. So we compute the mid value, which is lower bound plus upper bound divided by 2. Then we see if our function evaluated at midpoint falls within the specified threshold. If it does, we have found the root value. If it doesn't, then we see whether the sign has changed in that interval. So we first look at the lower bound and the midpoint interval. If that is less than 0, we update the upper bound to midpoint value. If this condition is not met, then we look for the upper bound and the midpoint product. If that is less than 0, we update the lower bound to midpoint value. And we continue like this. So if the iteration exceeds the maximum iteration, we come out of this loop. And if we exit this loop without returning any root, then we can simply return none. So let's run this cell now. And now here I am taking the information from root info, so how many roots are available, so that is at index 0, and then at index 1 we have list of lists. So that's how we will extract the information. We call the bisection method, we provide the function, and then we provide the lower and upper bounds of the interval from the root info. And let's run this. So we could confirm that our bisection method successfully identified 2 roots for this function, one at x is equal to 2 and the other one at x is equal to 5. Now let's see another method which is known as false position method. It also belongs to the bracketing method and it is also known as linear interpolation method. So here the difference is that instead of the midpoint calculation, we estimate root from the linear line drawn from the start to the end of the interval. That's why we call it linear interpolation method. And the subinterval where the sign change occurs, again it's selected and we repeat the process until a stopping criterion is met. So this is the interpolation formula, and that's how we update the root. Again, if we look at the false position method code in Python, the input arguments remain the same. The only thing that is different from the bisection method is that interpolation formula update. So here, instead of recalculating the midpoint by taking the lower bound plus upper bound and dividing it by 2, we are using this interpolation formula to calculate the midpoint. So if rest of the code remains the same, so I won't go through the entire code again, but let's run this cell. And again, this part of the code where I'm calling false position method and giving the function and its lower and upper bounds for the interval to see if it retrieves the correct roots for the function. Again, we got the correct roots for the function. Now let's move on to see the open methods, and the first open method that we are going to see is Newton-Raphson method. It is one of the most frequently used algorithms, and the entire algorithm works like this. So we pick an initial guess, so we don't have to provide an interval, lower bound or upper bound, we simply provide an initial guess, and then we draw a tangent line. Next guess then will be where the tangent line intersects the x-axis, and then we repeat this process steps 2 and 3 until a stopping criterion is met. So this is the Newton-Raphson formula. So x sub I plus 1 is equal to x sub I minus f of x sub I divided by f prime of x sub I. So here is the derivative of x. So this is the Newton-Raphson function. It requires the input function, its derivative, and then the initial guess x0. Again, as a stopping criterion, we need to provide a threshold and maximum iteration. So we start with the iteration 0, we set the initial guess value as x, and then we run this infinite loop, and here we have the update formula. So once we have updated the x value, we evaluate that function and then check whether the function value falls within the specified threshold. If it does, then we have already found the root and we exit the function. If it doesn't, the loop continues until we reach the maximum iterations. Okay, so let's run this function, and now again we will run the same function on the root info. So here, since we don't need to provide the lower bound and upper bound, so we are calculating this guess value, which is the midpoint of those lower and upper bound. But you could provide any initial guess that is closer to the actual root value, and the function should be able to find the root values efficiently. Okay, so let's run this. Again, we find the two roots, x is equal to 2 and x is equal to 5. Okay, so the next method in the open methods category is the secant method. It's very similar to Newton-Raphson method. It, however, requires two initial guesses, but these two initial guesses, unlike bracketing method, they don't need to surround the root, so we just need to provide two initial guesses. So here we approximate the derivative using a backward difference approach. So this is the update formula. So let's see how we implement this secant method in Python. So again, we have the function as the argument. Here x0 and x1 are the two initial guesses, and again we have the stopping criteria, threshold and maximum iterations. So we start with the iteration. Again, as you can see, the function is almost the same as the Newton-Raphson. So the only thing that we are changing is the secant update formula, and that's the same formula that we have written here. And we also need to update x0 and x1 after every iteration. So once we complete this loop, either we will return the root or we will return none as the answer. Let's run this cell, and again we'll run the secant method, the call to secant function, and if we run this, x is equal to 2 and x is equal to 5 are the two roots, and that is the correct answer. The next modification is the modified secant, and that also belongs to open method category. And unlike the secant method, it requires only one initial guess, and it requires another parameter, which is a perturbation parameter. And this is the update formula for the modified secant method. So let's see how we implement modified secant method. Again, the input arguments are the function, x0, the perturbation, and the stopping criteria. So we start with the iteration 0, x, and set x to x of 0. And here again, the only difference from the Newton-Raphson implementation is this modified secant update formula instead of Newton-Raphson update formula. Once we run this cell and run this function on the roots info, we get two roots correctly, x is equal to 2 and x is equal to 5. Okay, so these were the 5 or different root finding methods. These are very useful methods. I hope you like this video. Please continue watching other videos on my channel as well, and thanks a lot, and see you all in the next video.